Welcome back. We said at the end of our last video that there were two decent ways of trying to represent a number this big or this small, such that we could actually conceive of it a little more effectively. And those were to use scientific notation or to just simply use a different unit. So we're going to start with the first of those. And examine how I turn this into a scientific notation representation. Essentially, the idea of scientific notation is I'm going to make my final number look like this. And what we have here is a number between 1 and 10. And I'll make it even a little more specific. It can be exactly 1, but it cannot be exactly 10. It can be as close to 10 as we like, but cannot be 10 on the dot. That first number is going to be that, and then that is going to be multiplied by a power of 10. And if this is a little bit new to you, when you see 10 raised to something, that simply means 10 multiplied several times, however many times it says here, by other 10s. What we're going to do is take any number like this and break it into those two pieces. And I'm going to start simple. I could say this is 1,400,000 times 10 to the 0. Because 10 to the 0 means I'm not multiplying by 10 at all. Anything raised to the 0 just equals 1. So notice that at the moment, this has the same value as what I started with, because this thing right here equals 1. What I'm going to do is, because I want this number to get smaller and smaller, I'm going to start peeling off 10s and putting them into that power of 10. So for example, I might start by saying, let's make this 10 to the first, so just a single 10. Well, if I want the whole expression to still equal 1,400,000, then I need to divide this thing up here by 10. In other words, I'm going to divide this part by 10, multiply that part by 10, and the whole thing stays the same size. So this would now be 140,000 times 10 to the 1. And if I keep doing that, I'm just going to keep lopping off zeros. So notice if it's 10 to the second, now this is 100 times 14,000. If you do that math in your calculator, you'll see that it comes to 1.4 million. And I can keep on going down. 1.4 times 10 to the 6th, and notice that when I reach that spot, my other condition has now been taken care of. I need that first number to be between 1 and 10. Once I get that, I stop putting in new powers of 10. If I think of this another way, what I essentially did is I took the decimal point that was here and I bumped it 6 times, right? 1, 2, 3, 4, 5, 6. Until it now lives right there. And as a result, I have to multiply back the 6 10s that I got rid of as I kept moving that decimal point around. So we're going to try the same thing here with 18C. This one was 18A from your textbook. 18C is going the other direction. So notice this time around, if I want to make this into a number that is between 1 and 10, I'm actually going to have to multiply it by 10 several times. Which means if I start like this, I am going to have to multiply this by 10, which means dividing that by 10. And so in other words, I could make this, in fact, I'm going to try it a slightly different way here. I'm going to write it this way, times 1/10. Okay? Although admittedly that was originally 1/10 to the 0. Okay? And so if I now multiply this by 10, so I'm going to get rid of one of those zeros. This becomes 1/10 to the 1. If I get rid of another 0, and lastly, 3.54 times 1/10 to the 6th. Okay, so notice I've gotten my condition met again. But this isn't generally how you see it written. When I say that I've got 1/10 to the 6th, we also represent that as 10 to the minus 6. And that's how we're going to write that number. Notice here again, it's the same number here as the number of times I bumped the decimal point. So again, I went from this original spot, 1, 2, 3, 4, 5, 6. to plunk that decimal point right there. And I kept doing it until I wound up with 3.54. That's the essential idea here. And so, for example, if I want to go the opposite direction and actually create a standard notation number out of something that's in scientific, notice that because this is already 7.4 times 10 to the minus 2, what that really means is 7.4 times 1/10 times 1/10. In other words, that decimal is going to move once, twice, end up here with a 0 in between. And so 7.4 times 10 to the negative 2 is just going to equal 0.074. And you can convince yourself of that by redoing what we did here to show yourself that when you move this twice, you get back to 7.4. So before we move on to the other units, I'd encourage you to try to come up with these scientific notation results on your own. Pause the video, and when you come back with a snap, we'll see what the real answers are. Okay, here we go. Okay, that's what we've got. Hope that matches up with what you came up with. I do want to point out a couple of things. Notice how all of the trailing zeros and all of the leading zeros in these big numbers and in these small numbers go away when you do scientific notation. If I'd had a 0 hanging out here after a decimal point, and after the first non-zero digit, I might have needed to include that. But the great thing about scientific notation, along with making the number easier to look at, is that it's also going to get rid of all of those extraneous zeros that didn't count as sig figs in the first place. And I, for one, say good riddance. Now, I mentioned at the start of the video, the other way we can do this is by incorporating metric prefixes into our tool set. And metric prefixes are a way that we can take an individual base unit, something like, say, a meter, or a second, or a liter, and make it bigger or smaller to suit the size of the thing we're actually measuring. So if I want to make something bigger, what I can do is say, well, what about a unit that's 1,000 of that thing? When I have that, what I'm looking at is kilo, or K, generally as the abbreviation. And so a kilometer would be 10 to the third meters. So when we talk about distances on roads, we tend to use this unit because it matches up better with the size of the thing we're measuring, rather than talking about how many meter sticks I need to stretch to get from here to, well, school. If we want to keep on going up higher, we get a couple of things that you might find predominantly in computation: mega and giga. Notice that is a capital M and a capital G. Those are 10 to the 6th and 10 to the 9th, 1 million and 1 billion. Getting much, much bigger. So if I had, for instance, a megameter or a gigameter, those might be things that I could measure celestial distances in, because they would be big enough to handle that. If I go back the other direction, we've got a few as well down here that can be smaller. And so here we're going to be doing the 10 to the minus sorts of units. 10 to the minus 3 is milli. I'm not going to put it there. I'm going to put it here because it's a prefix up here. Milli, M-I-L-L-I. And so if I have a millimeter or a millisecond or a milliliter, those might all sound familiar because those are all things that we tend to measure on a regular basis, things in that size scale. Again, each of these will be 1,000th of that. If I want to keep going, 10 to the minus 6, 10 to the minus 9, I can. 10 to the minus 6 is a prefix called micro. We actually use a Greek M or a mu for that one because, as you'll notice, we've already run out of the other M's that are available. Really, it's just a lack of imagination, if you ask me. A lot of different units that, for some reason, all start in M. 10 to the minus 9, think old iPods. That's nano. And so when you hear that, that is 1 billionth. It is as small as giga is big. Micro is as small as mega is big. There are two others that you're going to see that are in between milli and the base unit because those can sometimes be useful. We've looked at one of them already. C is centi, and that's 10 to the minus 2, or 1/100th. And then deci is D, and that's 10 to the minus 1, or 1/10th. You'll sometimes see deciliters show up when we talk about dosages. A very common dosage is, or a measurement or a dosage unit is milligrams per deciliter. So in other words, thousandth of a gram per tenth of a liter. A lot of times the number comes out very useful in there. So these two are sort of oddballs. All the rest of them, you'll notice, are not even just powers of 10, but they're powers of 1,000. So we go 1,000, million, billion, thousandth, millionth, billionth, two weirdos in the middle right there. So I'm sure the question you're most interested in is, which of these are you going to be responsible for knowing? And the answer is these 8. Those are the ones I'm going to hold you responsible for. Don't worry about any of the others. They do keep going, both in the small and large direction. If you take a look at these right here, pico, femto, atto, zepto, yocto, that's 10 to the minus 12, 15, 18, 21, 24. Same thing if I go for large ones. You might have heard of terabytes or petabytes when talking about large amounts of data. This might be what's on an external hard drive. This is what servers tend to contain. It also goes to eta, zeta, yata, also going up towards 10 to the 24th. Actually, when I was in graduate school, there was a neat petition, which has my signature on it, because I love few things more than just linguistic science humor, to make 10 to the 27th meters equal to 1 helimeter. And it's a real shame that the Système International did not adopt it. Clearly just not French enough. So what we're going to try to do on our next video is take those units, those prefixes, and use them to turn these into much more manageable numbers. And we're going to do that by deciding on a better unit for each of them. If we think about what we did with scientific notation, we can get a sense of what some of the better units might be. This was 10 to the 8th. This was 10 to the 4th. This 10 to the minus 2. This 10 to the minus 5. This is 10 to the minus 21. Each of these things here would benefit from a unit that's near that same 10 to the minus. So for instance, the Earth to the Moon distance might work better in gigameters or megameters. The DVC to San Lorenzo distance almost certainly done most effectively in kilometers. The thumbnail, 10 to the minus 2, well, that's easy. We'll do that in centimeters. The hair, 10 to the minus 5, that's in the vicinity of 10 to the minus 6. We'll try and do that in micrometers. And the proton, to be perfectly honest, we could go down to nanometers, but it's barely going to make a dent in it. And so just for the lulz, we're going to go ahead and do that one in a different unit. We're going to try that one in zeptometers in the next video when we learn how to do conversions.